Hi everyone. In this session, we will be discussing about CPU scheduling. This is the first part of a series of videos that will be created related to CPU scheduling. In today's session, we'll discuss some basic concepts related to scheduling, and then we'll discuss one of a very simple scheduler. So the very first concept that we are going to discuss is like the number of tasks that needs to be scheduled is always more than the number of cores available or the number of resources available. So this is the reason you need a scheduling. Like you have so many tasks, how efficiently you can allocate them to the resource. That's the aim of scheduling. So one simple disclaimer here. So like throughout this presentation, I might interchange the term task, jobs, threads. All these terms means the same. So now the next concept that we are going to understand is about CPU burst and IO burst time. But before we go into the burst time, we need to understand something about IO. IO doesn't use CPU. For example, whenever you write something to a file, whenever you write to a file, it is the disk controller that is being utilized. It's not the CPU. Similarly, when you write something to the network, it's the network controller that takes care of the activity. It is not the CPU. So if a thread needs to perform some kind of IO, then it doesn't use any CPU. So this thread can be uh, moved out of the CPU and we can schedule some other thread. We can allocate some other thread to the CPU, right? So now coming to the CPU and IO burst time, right? So like all the threads, most of the thread follows this pattern where for a few seconds they want peak CPU usage. After that, they alternate to peak IO usage. So here in this diagram, in the top quadrant, I have represented the CPU burst, and in the bottom quadrant, I have represented the IO burst. Next is scheduling incurs cost. Scheduling is not free. See, for example, the algorithm that the scheduler uses to pick the next thread is to the CPU to send it to the CPU, that might take some time to execute. Another thing is whenever there is a scheduling, whenever there is a rescheduling or whatever you call it, like you're doing a context switch. So if you do a context switch, obviously the overhead with context switch costs time. For example, the memory segments has to be remapped. And also another thing is you need to rebuild the cache. The whole thread would have like populated the CPU cache with its own memory data. Now you have to validate it and then you need to rebuild it as per the new thread. Now let's discuss about a thread state mission. First, let's analyze what are all the possible states that a thread can be in. Ready? This is the initial state whenever a thread is ready to start. Then this particular thread will be in the ready state. Ready state usually means this thread is part of the ready queue of it's part of a queue maintained by a scheduler running. This thread is being executed in a CPU waiting. Probably the thread is performing an IO or the thread is waiting for some synchronization with other thread, maybe related to logs or something related to join. The final state is terminated when the thread has completed its process. It goes to the terminated state. Now let's look into how what are all the transitions that happen between these states. Whichever thread, one of the thread which is in the ready queue is put into running state by the scheduler. Actually, scheduler performs this transition one. Running to waiting, as I told you, whenever an IO happens, the thread reaches the waiting state. Waiting to ready, after the IO is over, the thread would again come back to the ready queue. Then scheduler will send it to the CPU at the right time. A thread, after completing its process, will move from running to terminated state. So the final transition is from running to ready. This particular transition happens only if there is a timer interrupt available. So whenever a timer interrupt goes off, whichever thread was running, it will be moved from running state to ready state. The reason we are doing it is once it has moved to ready state after timer interrupt, the scheduler has the option of scheduling the same thread once more to the CPU or scheduling some other thread to the CPU. Now let's discuss about two major techniques in scheduling. First one is called non-preemptive scheduling. In non-preemptive scheduling, whichever thread is running, it will not, it has to yield the CPU. When it is running, it will not be forced out of the processing. It has to voluntarily yield the CPU. For example, in this case, whenever the thread goes to terminated state or whenever the thread goes to waiting state, then then the scheduler will choose another thread. But when it is in running, like it can run its task till it can completely run its CPU burst. Next, the other technique is preemptive scheduling. This is the exact opposite of non-preemptive scheduling. Even when the thread is in running state, using a timer interrupt, as I explained above, like that particular thread can be interrupted, and the scheduler can choose to schedule a different thread. Let's look at the targets that we achieve to reach using scheduling. The first target is throughput. Consider two threads, thread X and thread Y. They have substantially large CPU burst time and IO burst time. You can assume they are two batch processes. So in a batch process, what do you expect? You want the batch processes to complete as fast as it can, but you are not waiting for a sub-second response. There is no end user waiting for a response from the batch process, right? So in this case, if you want to have a maximum throughput, then the the number of scheduling activity you perform should be kept to a minimum. In this way, the scheduling overhead will be reduced and you will be able to achieve a maximum throughput. Now, but consider the other case. For example, thread X is a batch job and thread Y is something related to a transaction-based system, OLTP kind of system. Here, maybe a UI thread it is, and the user is waiting for some response back, right? So it has short CPU burst, short, very frequent CPU burst. So now, in this case, in this case, if the scheduler is first going to schedule the thread X, and then it is going to put because it arrived first, and then it is going to put thread Y, then the system is not going to be responsive. The thread Y is going to wait for a long time, right? So if response time is the target, then it makes sense for us to do frequent scheduling or frequent context switch. There are a couple other targets that can be aimed for. One is the average wait time. See, wait time is the amount of time a thread spends in the waiting state in the scheduler, or the amount of time that its thread spends in the ready state. That is the wait time. Average wait time is the average time or average wait time for all threads in the system. Uh, there are a couple other targets. One is priority. Maybe it can be user defined or it could be system generated priority. Another is energy consumption. If you want to keep the energy consumption to a minimum, what is the scheduling strategy you should follow? Okay, the scheduler that we are going to look today is called first come first serve. This is a very easy to implement scheduler. All that it does is like it maintains an internal queue data structure, and then like it keeps track of whichever thread that has arrived first, it will schedule it first. And this is a non-preemptive scheduler. So like whatever thread it has assigned it, that will run till its CPU burst is CPU burst is completed. Let's look at an example of how this scheduler works. Now, consider this case. Assume there are four threads that are being uh, uh, that has been sent to the scheduler. So, for clarity's sake, like in this case, let's forget about the I/O burst. We just have considered the CPU burst. The T1 has a CPU burst of 15 seconds, T2 15 seconds, T3 10, and T4 is 5 seconds. Now, how is FCFS is going to schedule these threads? T1 arrived first, so it is going to schedule 15 seconds to T1. After 15 seconds, T2, followed by T3 and T4. Now, let's calculate the average waiting time for these threads. First, for thread T1, yes, it was immediately scheduled. So since it was the first thread, so there is no waiting time. For the second thread T2, it actually arrived at 5 seconds, and but it was scheduled only at 15 seconds. So the waiting time for that thread T2 is 10. Then for similarly for T3, it comes to 20, and for T4, it comes to 25. Again, you see here there is a 25-second wait time for a short burst, for a short CPU burst. Probably this is a UI thread, but it is made to wait for 25 seconds. This is one of the major drawback of FCFS. Now, if you the average waiting time, if you want to calculate for this system, it comes to around 13.75. Another disadvantage of FCFS is a phenomena called convoy effect. So, what is a convoy effect? See, a convoy effect occurs like, for example, there's a long job that a CPU is executing. So, because of this long job, multiple shorter jobs or multiple jobs which arrived a little late or in the wait queue. Now, these jobs in the wait queue probably they have a shorter CPU burst, but they have a longer I/O burst. So these jobs which should ideally be executing I/O, which should ideally be performing I/O, is being blocked in the CPU wait queue. So now the I/O is idle. But after the time, like whenever this job is completed, then there will be a contention for the I/O. This is called as convoy effect. Let's see that with an example. Assume there are two threads again. Thread one is with a longer burst and thread two with a short frequent burst. Thread 1 has arrived first, has arrived at second 0. Now, if FCFS has to schedule it, it is going to follow such a pattern here. First, it's going to schedule the thread T1, let's call it T1, followed by the other thread. So now here, if you see here, for this particular 10 seconds, whenever T1 is executing in the CPU, IO is idle. Nothing has been passed to the IO. But again, now the reverse happens whenever this thread, if in case if this thread goes and blocks the I/O, at that point the CPU is kept idle. So like this, though there is enough amount of work to be executed, CPU and I/O are alternatively kept idle. This doesn't look like efficient, right? Efficient approach to schedule it. Now, so in case if we want to schedule it effectively, probably like let's look at these types of scheduler in the later sessions. But for now, let's understand how will it be if we want to efficiently schedule it. What we can do first thing is probably we can do preemptive scheduling, and then probably you can swap it. You can swap the two processes. So then what happens? You can see the amount of time the CPU or IO is idle is kept to a minimum. So in FCFS, so for example, in 40 seconds, probably like you did effective work only for 22 seconds. Rather here you did 31 seconds of work. But yeah, I mean, obviously, like for this scheduler, like we have not considered the context switch overhead. Finally, let's analyze one of a job pile-up scenario in FCFS scheduler. Uh, Consider this is how like you receive the input traffic. On the one hand, you have a stream of threads, right? So like let's assume it's an infinite stream of thread. Like the incoming rate is like you get four threads in a span of 5 seconds. In every 5 seconds window, you get four threads. Like that, you continuously get a stream of input thread. On the other hand, like you have our typical batch process, which has a 20 seconds CPU burst, and then there is some break, and then again it has a 20-second CPU burst. Now, if FCFS scheduler is going to schedule it, like it is going to first, because since if you see here first the batch job are at first, so it is going to give priority to the batch job. But since it does it, whatever in this interval, whatever the shorter jobs that have arrived, all those has been squeezed. And at second 20, like you have a contention between 16 threads, right? So on the other hand, like if we were to do like our common way of doing a better scheduler, probably you give a you give more priority to the shorter the stream of shorter jobs. In this way, like your so in this way, like your system is going to remain stable. The number of waiting jobs can be kept to a minimum. See, one important thing here is like even like I was of the assumption like since the jobs at second 20, 16 jobs have been piled up and have been in contention. So now as the time goes by, I was expecting this number to blow up and then crash the system. Right? So let's plot a graph and then see how the system behaves actually. In case of FCFS scheduler, if this is the traffic pattern. See here, this graph, it's actually the x-axis is the time unit here, and the y-axis is the amount of time you can say for short jobs and long jobs. You can say this is the amount of time that has been spent for the short or the long job. In case of waiting job, you can also consider this as the number of jobs that are in waiting y-axis. The red color is the red color line is the number of waiting jobs. Surprisingly, you could see here the waiting jobs didn't blow out of proportion. It seems to remain constant, right? And another thing is like the actually the number of short jobs that are being executed is far more than the number of long job that is being executed or the amount of time that has been spent on the long job. Why is this the case? Right? So here, see here what you have done is the first when the FCFS schedules the first burst, yes, the long job has been given priority. Now at second 25, actually the second burst is ready to be scheduled, but it will not be scheduled immediately because it's first come first serve. So this particular burst has to go to the end, right? And it's not even after at point 36. Maybe by this time 5 there would be 4 more. So probably at around 40, 41. That is the time the second burst of the long job would be scheduled. So now I hope you see the relation here, right? So like as the amount of jobs piles up, the the delay in which you schedule the long job that also increases. On the other hand, If you keep scheduling the shorter jobs, actually, so for example, if this is the way you're going to schedule, so the consumption rate by the CPU would be around, say, like 5 jobs in every 5 seconds. But our incoming is actually only 4 jobs in every 5 seconds. So the number of waiting jobs is going to reduce, right? So this synchrony between these two ensures that actually the app doesn't crash. So let's see the long job and waiting job alone in some more detail here. Like when the long job is executing for the first 20 seconds, the amount of waiting job increases. Now the long job is not executing. For a few part of this time, it's actually waiting for the whatever it's IO burst or whatever. After that, it is because it is later in the queue. So the shorter jobs have started executing. So you see, whenever the shorter job executes, the amount of jobs in the amount of waiting jobs has reduced again. So like this, it keeps growing. So now if you see here, as the amount of waiting job increases, the delay between the two long job also increases. In this way, the system it's kind of like reaches the the waiting job kinds of reaches a equilibrium around some 40-60 range. So and then it stays there at that time. So okay, so this is the site I had referred to the content for today's video. So that's all I had for today's session. Like I'll create videos for other schedulers in future.